Okay, now let's move to the main content, Lecture 1, Introduction to Optimization. We will have the introduction first about the main content to tell you what is optimization, why do we need to do that, and how to conduct an optimization problem. The course goals and topics, especially the learning objectives you are aiming to achieve by end of the lecture, and some class schedule will be discussed in this video. Also, some general examples, such as the linear programming, the least square problems, convex optimization, will be briefly discussed. These are all classic optimization problems. We will touch more details later in this lecture. But this first part is just to give you a general sense what is different types of optimization problem and how they are commonly used in our work and life. Finally, some applications in engineering, not limited to chemical and biological, will be discussed to show its linkage to your background, to your major. So first of all, what is optimization? You might have used the word optimization, optimal conditions, in many occasions. In your life, in your experiment, when you optimize the conditions, it's always some extreme points, either maximize or minimize the value. But how do we search for these optimal points? So those GIF will give you a basic sense when we solve the optimization problem through mathematics to find analytic solution or through programming to get the numeric solution. The target is to find this peak point, for example, this one to give you a maximized point, and this heat map is to show you the minimum point over the grid, over the value. So it shows different algorithms how we find this optimal point by iterative searching. So how they find the path. Think about you climb a mountain or do some hiking. You got no clue where to go. There is no clear path, or there are multiple paths you can choose from. Therefore, to go to the peak, to go to the summit, you need to find the proper way. With some constraints, you need to be safe, you need only go on the paved path, or some additional objective to have minimized energy used or the other conditions. But considering all these constraints and objectives to go to the peak point, the process can be valued as optimization problem. And the solving process is how you search for the best path that meet your goal, the best direction. At each step, you search for the next direction to go find the optimal point. Okay. So this is what is optimization. It's commonly used in the design, operation, all kinds of problem. So operations research is a background. We got a scientific approach to decision making. The final goal for optimization is to support our decision making, to make a decision what to eat, what to put in your bag, what to buy in your portfolio, which way to go in the hill climbing, and then decide the best strategy for a system to allocate scarce resources. So this is quite important. This problem nowadays, if we have limited resources, how we get the best strategies to maximize utility. So in the mathematical term, it just means to determine the value of variables. So those variables are those that can change. Normally we indicate them by value of x, by different, like it means these things that can vary, that can change, like how many apples you put to your basket, when you want to go to a supermarket to buy for your next day's meal, or which way to pick if you have 3 ways in front of you when you climb the mountain at a certain point. So those are the variables. That means you can change that. You can choose one from all those either continuous or discrete variables, which minimize or maximize the objective. So think about minimize and maximize. This interesting point here. If you want to define a minimization problem, normally our strategy is always just to minimize some objective. But it's the same procedure if we want to solve a maximization problem. Because in order to minimize one value, it's the same to maximize its negative value. So this is a point we will commonly use. The minimization and maximization problems are always solved in the same way. So if you want to get the minimum value of y, for example, so y can be a function of all your variables. So we are familiar with the way y, x. So if you want to write this minimize y, it's equivalent to the maximization problem. What? So maximize negative. So this magic sign, negative sign, negative y, x. Right? Think about this. This will be very commonly used because then you will only consider minimization problem. You will be able to solve all the maximization problem as well. If you want to minimize your cost, it's positive cost, total cost to buy some stuff. It means you need to maximize the minus cost. So it's 0.1, this is minus 0.1. If it's 0.01, it's smaller, and it's minus 0.01 is larger. So it's the same way to form the problem. Okay, so that's objective. But in the meanwhile, we need to satisfy all the constraints. That's constraint. Okay, so it's also to satisfy all the constraints if there are any constraints. Make a constraint optimization, or if you have no constraint, like the problem of least square we'll discuss later, it's also unconstrained optimization. It's a basic problem formulation we will discuss in lecture 2. And then the format to really write down this optimization problem in the mathematical format, we will use this again and again in our problem formulation. It's basically 2 parts. So you have objective written subject to constraint. If we read carefully, we can have this, as we discussed, min and max are the same way to be solved. So you can write as min objective function here, z. So z is a function of your variables, x and y. Or as we written before, the symbols are interchangeable. You can use y as your objective function as some f function of x1 to xn, or any symbols you can use. But here the objective function is written as a function of the variables, which means this is the target to be minimized, or the same way to be maximized. So here's some examples. If you formulate that, we can minimize our cost for a decision problem, for your budget planning, for your inventory planning, your planned operation in your design project. Or minimize the environmental impact. Nowadays, we concern a lot about the sustainability issue. So we know the CO2 carbon emissions are a huge issue to cause climate change. Therefore, in the process design in many of the process level operation, we will consider how to minimize the environmental impact by minimizing the CO2 carbon emissions. So that's all kind of objectives we will consider. And the constraints, here we use subject to, so it's a ST as a symbol to say. Now I will start to write my constraints. So think about constraints. It can either be some of the equalities, equations, like all you learned in the previous course. You learn heat and energy balance, mass and heat transfer. These equations you learned are some more general about your constraint of the budget. So those things can be the equations for your model, for your optimization. You use the equal sign here. So you can move all parts. It can be any equations and move all parts to the left-hand side. So right-hand side becomes 0. The written way is any way is okay. This means these are the equality constraints to the model. But more commonly see are those inequalities. Like we see the budget, if you put it as an equation, I have $100 to be spent in the supermarket. You can see I put the equation, I make all the stuff sum up to be 100. But normally it's easier to solve if you put this as an inequality constraint. You can see all my stuff I purchased in my basket will be smaller or equal to $100. So just move the total value, the total of your, still use a very easy example. If you buy things from the market, for each term, it will count. So this is sum then for each unit item, it got to a cost of, let's say C. So C is a parameter we know it's a unit price for a product, example I, and I want to decide how many items I buy in this market. So I can use xi. So here you can see xi can be a integer, discrete value. I buy 1 box of milk or 2 boxes. Or it can also be some continuous value. If you weight that, I buy 1 kilo, 1.2 kilo, or so it will discuss all those constraints later, how to write your variables. And then this value, because the total cost has the upper limit by the budget, if you know it's 100, or you can write it by symbols, it's easier. You just write this by your, define it as a total value you can spend, some symbols. So this becomes your inequality constraint. When you move this 100 to the left-hand side, it becomes the standard format. But you can write it, it's still solvable. You can write this as an equal sign if you want to use it to the maximized value, or you can say it's just a constraint. So this is a basic example to show. But when you use this in your process design problem, this inequality is very important. Sometimes when you see I have some process specifications like the quality, safety of a certain value for exploratory materials cannot go beyond certain maximized limit, you will use this inequality constraint. So this is something different compared with what we learn. If you just say the equality, it will be the same as what you learn in the basic engineering principles. It is all equal sign. But now if you got more inequality constraints, you will be able to use this kind of optimization setting to solve the objective, give you optimal solutions. Okay? And then it's also important we discuss how we define those variables. Either it's continuous variables, like we say the weight, temperature, flows. So here we use R, the real number in the n dimension. So it's a way you can write X is a real number using this way. So it means continuous here. This is continuous. Or it can, another variable here we use Y to indicate. This Y we put it belongs to 0 or 1 in the dimension of M. So this is dimension, you put it as an upper. If you write in this way, Y belongs to 0 or 1, what does this mean? So we know in computer language, it reads all the in the computers we now use, how it stores the memory. It uses all the logic decisions. So it captures this as 0, 1 to keep all the digits to compute large amount of the computing. So that's a very fundamental law of computer that's called logic decisions. We use this 0 and 1 as discrete variables. So basic example is mixed integer, it can be 0, 1. Or if you define it as integer variables, it can be 0, 1, 2, 3, 4, continuous, not continuous, but discrete integers. Or just 0, 1, we can call it binary because it's just two values. So it's a binary variable, or it's integer variables. So we will use this again and again. So I spend some time here to introduce you the concept, because this is a very basic format of optimization. Binary. So our goal is to have the decision variables to be determined. So they are to be optimized. They can change. They are to be optimized. Well, we have another term, parameters, like in the example, the 100, this M value. Those are the constant numbers which are given in our problem formulation. So those can be the parameters in the problem, or you can call it coefficients in the objectives and the constraints. So those are the numbers given, but not the very things to be determined. Like in the example, tell me, what is CI? What is XI? Are they variables or are they parameters? Think about this. So CI is a unit cost of an item it's given, and XI is the units to be purchased for each item. It's to be determined. Therefore, the unit cost is what you know before you solve the problem. So it's coefficients or parameters. But the XI here, the units you will buy are unknown, but to be determined from the optimization. So they are the decision variables. Okay, so this is a concept we need to keep in mind for optimization. Think about this. Okay, so after we see the mathematical formulations, we further emphasize why do we need optimization. As you see, it aims to select the best possible decision from a given possible set without having to evaluate all of the options. So what does this mean? If you know all the paths to go to the peak of this mountain you want to climb, you can calculate really all of the paths to there. However, you can think about the computing amount. If it goes to from the beginning to all the branches you can have, if you just have one or two options, it's easier. You can just calculate it through those different options. But normally, the problem has a lot of decisions to make. You can think just write the branch all the ways. So you think how many possible sites you will have. So when it's continuous variables, this is discrete, right? You can only choose left or right, 1, 2, 3, 0 or 1. But when it's continuous, you can choose from 0 continuously to 1. Then it's normally infinite options. You will not be able to calculate the corresponding value for each of these numbers. Therefore, you need these mathematical tools to find you this peak. So how to find the best path to go there, to go to this peak, is what optimization can do for you. Especially for nowadays in industry or daily life, you got limited resources, but multiple desires. So now the world has decreasing resources. Like for the young generation, the environment is no longer that abundant, that rich for us to do whatever you want to develop. It's limited resources, but the desire, human ambitions are increasing. You still want to be billionaire. You still want to use the limited resource to generate as much value as possible. So this increasing goal and decreasing resources make us, we must do optimization. It's very important for every person, especially every engineer if you want to work with industry problems, every scientist if you want to solve the nature's problem. So that's why optimization is becoming more and more important. Specifically in chemical engineering, it becomes a routine use for optimization in a wide range of processes. So many of you are doing the senior process design project. So when you study that, the synthesis and design, you can't do it by trial and error or by your expert knowledge. But through optimization way, it will give you additional insights, probably get the most appealing design among your peers. Also, the process planning, control you learned in previous course, this all involved optimization concept. And also in other industries, not limited to chem eng, if you study the aerospace or some logistics, the airline planning, supply chain management, especially in finance, when you do the portfolio management, and more broadly in those AI stage, machine learning and artificial intelligence, robotics, these all involve computing techniques, especially optimization. So we will have some lecture content covering how to do machine learning along with the optimization content. And you will see optimization is a very important element if you want to get a good machine learning model. Okay? So we want to give you a very brief history of optimization of this field. You can trace back to many of the famous figures from Newton, Fermat, in like how many years ago? Less than 400 years ago. This is very original development of optimization. But that's pre-digital computer era. It's not like today we solve all the problems in computers. That's from the analytics when you handwrite all the equations and solve that. Just many of them stay at a conceptual stage. They were not able to solve the large scale problem. But it's very important to get the concept when you have the function f(x), like a very basic one with a single variable x. The optimal point lay in x star, where this df over dx equals 0. So this is an important concept. This will be always used even in a very complex example. So think about the hill climbing problem again. This is your peak point, and it states that at the peak point, this first order, it should be a straight line, first order derivative should be 0. Right? Means this first order derivative is what? It's a slope for this tangent line, right? If you studied your calculus, you know the first order derivative, you need to draw a tangent line, and if this is a straight line, it means this is the optimal point. This is the basic concept. You have more development later on, but this is the very beginning foundation. So the mathematical world was developing quite slow in that stage. If we see from our perspective now, but it's still huge development. After 100 years, Euler gets a more advanced level optimization. They now get the vector variables. So these are the series vector. It's like several variables combined in a set or in a matrix way. Okay, so this is the format. So until Lagrange gets a final format of this optimization problem, the standard way, so it's just objective with the equation constraint.